One of the properties that separates alkynes from alkenes and alkanes is their acidity. So it happens that alkynes are much more acidic than alkanes or even alkenes. And we can actually determine this based on pKa. So if you're not accustomed to thinking about pKa and their values, you certainly should get used to thinking about pKa because this is how we determine how acidic something is. If we look at the pKa of ethane, so removing a hydrogen from, one of the hydrogens from ethane, the pKa is about 60. Now, I say it's about 60 because in reality, we have very few bases that could actually remove a proton. And because of this, it's not acidic. We say that it is not acidic. When something has a pKa as high as 60, 55, 60, we say it's not acidic. Comparing that to ethylene, the pK of ethylene is 45, and so we see that ethylene is a little bit more acidic than ethane, but still it's not acidic, right? Now, ethyne or acetylene has a pKa of 25. And here we're getting into the realm of acidity. Still, understand it's a weak acid, but something that has a pK in the 20s is weakly acidic, and we have bases that are strong enough to remove those hydrogens. And we'll get into what kind of bases can remove that hydrogen later on in the semester. But I'm just introducing you to the idea of pKa and kind of the values associated with them, right? So 45, not acidic. 60, really not acidic. 25, we're getting into the realm of acidity. And remember, pKa is a log. So that means that, there's a difference of 25 to 35 times that between acetylene and ethane. And so acetylene's 10 to the 25th times more acidic than ethane. 10 to the 25th, 10 to between 10 to the 25th and 10 to the 35th times. Again, why is there a discrepancy? Because we have a hard time measuring the pKa of ethane itself. But suffice to say, very, very much more acidic than that of ethane. Now, let's put this in perspective. When we talk about acidity, how does that compare to that of HCl? HCl has a pK of -8. So remember, the smaller the pK, the more acidic it is. HCl is very acidic, and it has a very low pKa. And therefore, we're not even in the realm of the acid strength of something like HCl. And as a matter of fact, one of the strongest organic acids is acetic acid, right? Carboxylic acids tend to be the most acidic compounds, although there are other compounds that are even more acidic than carboxylic acids. But to put things in perspective, the pKa of acetic acids about 5, so 4.8, right? So when we talk about that is a weak acid relative to HCl, but in terms of an organic compound, it's a fairly strong acid. And there's a lot of bases that can remove a proton from acetic acid. As the pKa increases, you're decreasing the acidic nature. When we talk about acetylene being acidic, it's still a weak acid, but it is acidic. And if we think about the reason for that acidity, is really an increase in S character. So again, we talk about bonds, the bond length and strength of an alkyne bond. We can also talk about the acidic nature of that. And the reason for this is if you again go back to the amount of S character in a particular orbital, if we look at ethane, ethane is sp3 hybridized. So there's only 25% of that sp3 orbital is S character, Right? There's only a little bit of S character, 25%, a quarter of it. When we move to ethylene, ethylene is sp2 hybridized, and therefore there's 33% S character. 1/3 of that orbital has some S character to it. And again, when we move to ethyne or acetylene, we have an sp hybridized orbital, and therefore you're talking now 50% S character. Remember the nature of an S orbital. There are no nodes to the nucleus. A p orbital has a node at the nucleus, and therefore electrons reside further, well, they don't reside further away. They actually reside closer to the nucleus, but their probability of penetrating to the nucleus is non-existent because of the node. In an s orbital, while the electron may reside further away from the nucleus, in fact, it can penetrate into the nucleus, and this lowers the energy of that orbital. So what happens is, as you increase the S character of that hybridized orbital, you increase the potential for the electron to be at the carbon nucleus. And what that means is then the electrons are further away from the hydrogen. In essence, you're increasing the electronegativity of the carbon. So the electronegativity of the carbon depends really on the hybridization. The more p character, the less electronegative. The more s character, the more electronegative, because it can hold those electrons in tighter. So the more electronegative that carbon becomes, the more acidic the hydrogen becomes, the easier it is to remove that hydrogen. And that's a very important concept to understand in terms of the properties. And we can kind of demonstrate that, you know, if we envision what's happening here with ethane. When I talk about acidity, I'm talking about removing a proton. And in order to do that, I need a base, right? So the base is going to abstract a proton. So the electrons are going to create a bond with that hydrogen, and then the carbon-hydrogen bond, those electrons in that sigma bond, are then going to move to the carbon. The result is I have an sp3 hybridized carbon, and therefore the electrons are going to go into that sp3 orbital. Right, so that's an sp3 orbital, and that's where the electrons are going to go in. So important to understand that. So, and of course, I get now Hb as a byproduct of that reaction. So that is an sp3 orbital. And when I look at ethyne, and I do the same thing, I react it with some base, remove the proton, the electrons from the carbon-hydrogen bond move to the carbon. Now I have a scenario where I have an sp orbital, and the electrons reside in that sp orbital, right? So sp versus sp3. Now the electrons can actually be stabilized because those electrons can penetrate into the carbon, into the nucleus, much better than the electrons in an sp3 orbital. And of course, again, we get, you know, an Hb as a byproduct of this reaction. So important, we can talk about the stability of the conjugate base. So the conjugate base is stabilized if the orbital has more S character in it.